So here we go, number 11. This is called, right here, this function right here, you're dealing with more than one function. This is called a piecewise function. Only graph pieces of it. All right? So what I want you guys to do is pay close attention to this equation and this x is less than 1. Go to your graphing calculator. All right? Hit y equals. And in the y equals button, hit alpha y equals enter. Now, Liz, do you have the equation for number 11?
Yes.
What is it?
X squared plus 1.
X squared plus 1. Now, in the denominator, not in the numerator, in the denominator, you're going to hit the second portion of it. So you're going to hit,
Negative x.
hold on, x is second math. Is it less than or equal to, greater than or equal to? Is it greater than? What is it? Less than? So number 5. So we're only going to plot points that are less than a 1. Okay? Before I hit graph, I'm going to go back and take a look at our problem here. There's our problem right here. So yes, so right now, look, right here we're at x is less than a 1. So now that I have that, hit graph, and I want you to take a look at your parabola. Notice, only part of it's being graphed, not all of it. If you want to see a better zoom, hit zoom 4. No, there's not. There, right now, it goes right here and it stops right there, right? Okay, so we're not done yet. Because we have another equation we have to type in. So let's go back to our problem and see where that is. That's actually where? Oh, negative x plus 3. So what we're going to do next, Ryan, is we're going to go to our graphing calculator. We're going to hit y equals. By the way, how do I get that fraction bar again?
Second y in
Alpha y equals enter. That's right, Corey. I heard you. Good job. All right, I'll give you credit. So we have negative x plus a 3. However, in the denominator, I have to say x, and what symbol am I going to use this time? Right.
Greater than or equal to 1.
So right, second math, I have to go to what number? Number 4.
Is your mic on?
Yes, the mic is on. See how it's recording right here? If you're wondering, whenever we're recording, if you look at the bottom left-hand screen, you will see numbers going up. Okay? Right here. And hit graph. Let's take a look at it. So this is called a piecewise function because you're graphing not the whole thing, you're just graphing pieces of a function. Now, let me explain to you really quick what's happening in this graph. That was the first one. So right here, Ryan, technically that hole right there is not being plotted where, by the way, that's where x is equal to a 1. However, if we were to go to our new graph, okay, so even though right there wasn't being plotted, what is being plotted in the red graph? That point actually is being filled in the red line. Which means even though that point wasn't plotted in the parabola, it is being plotted in the red graph. So therefore, the answer to this problem is this is actually continuous. All right? This is continuous. Now, to review, let's say you had something that looked like this. Hold on. Here we go. Let's say this was your graph. If that was your graph and that point was not filled in, the answer would be what's called point discontinuity. But because it was filled in, it's continuous. Not filled in, discontinuous. Filled in, continuous. All right? Now, what would be called jump discontinuity? Let me show you what a jump discontinuity would look like, okay? So I'm going to go to another screen here. All right? So, for example, let's say there was a point right here, and your line went up like that, then that would be jump discontinuity. Okay, so just point discontinuity. Right? No, this one on ours is actually continuous because everything continues to flow all the way through.
We have that.
All right, let's look at problem number 14 now. Scrolling down to number 14. Ooh. This one says what? Determine the vertical and horizontal asymptotes for the graph. So the first thing I want you guys to do is, first of all, write this equation down in your journal. Okay? I'm going to do for you right now is I'm going to factor the numerator for you. Okay? So x squared minus 4 becomes x plus 2 and x minus 2. All right? In the denominator, x cubed minus x squared becomes x squared times x minus 1. So I'm going to highlight those so you guys understand. This factors to this. This factors to this. So now you have everything factored. Okay?
How do you know how to factor?
How do you know how to factor? Well, that's what we learned in Algebra 2.
I didn't know. A few years ago.
Now that we have it factored, we can actually locate our vertical asymptotes pretty easily. All right? So my vertical, VA, short for vertical asymptotes, it's where the denominator is made equal to 0. What number could I plug in right there to make the denominator equal to a 0? Correct. 1. Right? I'll catch you next time. Just so your hand get raised. So one of them is at a 1. So I'm a vertical asymptote at a where x equals 1. Now there's another number I could plug in here for x squared. I could put a number in there that would make that whole denominator be obliterated. 0, that's right. So the other vertical asymptote on this is x equals 0. So technically I have 2 vertical asymptotes because I made the denominator equal to 0. Now, there's a rule for the horizontal asymptote. Okay? You'll notice this number has a 2 right here. That exponent is squared. That number right there is being cubed. Right now, if I compare the end value to the end value, in your notes, that's our end value. In your notes right there, that's the end value. You'll notice that the end value is what? Less than 2 is less than 3. Now there's a specific scenario where when the end value is less than the end value, we know what our horizontal asymptote will always be. 0 is correct. So we know we have a horizontal asymptote at y equals 0. Okay? Now you can graph that out and try to figure it out. Let's go ahead and graph it and see if we can figure it out, even if you didn't know how to factor and how to do it. See if we can still figure it out. So right now, I'm going to go to the graphing calculator. Isabel, can you help me type things in? All right, I got to clear this out though. Clear it out. Clear this guy out. So we only see one thing. So I'm going to hit alpha y equals enter. And in the numerator, I know it was x squared minus 4. But what do we have in the denominator? X cubed minus x squared. Okay? So I'm going to hit the graph button. Let's take a look at this. All right. Now, understand one of the things I said was going to happen. We had a what? We had a horizontal asymptote right here. You see how these get really, they kind of stay really close to that. Now, remember I said most of the time they don't cross, but there are times where it does cross over, but then it just hugs that line. So that's your horizontal asymptote at y equals 0. What was it? What was one of our vertical asymptotes? At where? 1 was at what? 1 was at 0, right? And 1 was at a 1. Alright? So you see how this one gets really close to this? This one gets really close to that one. So those are our two vertical asymptotes.
Put that in the y equals
Alright? So understand, it's a little bit harder to see it when you're looking at the graph. It's a lot easier to see when you're looking at the equation. Alright, 12 and 13. Let's take a look at 12 and 13. Alright, number 12. What I'd like you guys to do on number 12, it says, determine whether each function is continuous at the given point. Alright? If discontinuous, what type of discontinuity it is. So listen, here we go. We have f of x equals x squared minus 9 over an x plus 3. Okay? Now, let me explain to you how to factor the numerator. The numerator is going to factor to an x plus 3 and an x minus 3. The denominator just stays x plus 3. Now, so here's our new equation with everything factored. So once again, I'm going to highlight something. This right here factors to this. Now, something interesting happens here. Yeah, those cancel out. What cancels out? Those x plus 3's cancel out, don't they? All right. So we're left with this. F of x equals x minus 3. Which that right there is just a line, right? Let me tell you something. Watch what happens when we type this into the graphing calculator. I'm going to go over here and clear this out. Alpha y equals enter. I'm going to type in x squared minus a 9 in the denominator. I'm going to type in x plus 3. Does that look like a complicated equation? It looks kind of complicated before we did all that stuff. But look what happens when I hit graph. Sure, alpha y equals enter. Alright, so what do you have? You have a line. And where are we supposed to evaluate it at? Where x... Where are we supposed to evaluate at? Where x is equal to a what? Watch what happens. Second graph. Look where it happens when x is equal to a negative 3. What does it say? It says what? It says error. Now let me explain to you what that error means. The error is not an asymptote. The error is a hole. There is a hole in the graph. So if I hit graph, alright, I'm going to hit trace, and I'm going to press enter. Oh my gosh. I think I see something. Bill, you see something? He sees something. I see something. That's Philip, right? Right there, everybody, in our graph, there was a break in the graph where? There was a break in the graph where x is equal to a negative 3, which means that's where the hole in the graph is. Now, what type of discontinuity is a hole? A hole is a line, a point, or a jump. What's a hole? That's point. This is called point discontinuity. By the way, there's only 3 options when it comes to discontinuity, all right? And if you're wondering what those 3 options are, let me relieve you of your anxiety. I'm going to highlight it. It says if discontinuous. I gave you a hint. It's either point, jump, or infinite. So if you forget those are your 3 options. No. All right? Infinite, listen. Infinite, it just doesn't cross. It's like an asymptote. You see an asymptote that is vertical, which is a vertical line, okay? That means it's going, infinite. Yes, infinite discontinuity. All right? And last but not least, what number do you need? 13.
And you go back to where you